All right, this film is going to help us understand the difference between exponential growth and decay. Go ahead and take a second and type the functions that you see here onto your calculator and see what kind of graphs that you come up with. Also see if you can notice what's the difference between the second and third graphs as compared to the first graph, a graph that you should hopefully be familiar with having studied exponential growth previous to today. All right, I've got all three functions graphed here, and notice that all I did was plugged in some easy points, plugged in numbers like -1, 0, and 1 into each one of my graphs and plotted the points. All three functions are just exponential functions, so there is no such thing as an exponent that will ever give you a negative base value or turn your base value into 0. Therefore, all the functions have a range that's all real numbers. I can use whatever I want, but a domain that's greater than 0, because there's a horizontal asymptote for each of my graphs at y equals 0. The major difference between the three graphs is that the function over at the left is exponential growth, because from left to right it starts out near the asymptote and grows away from it. Remember that 2 in the base is greater than 1. 2 to the power of x tells you that this is going to be exponential growth. The next two functions, on the other hand, go away from the asymptote down toward it. As you move left to right, we're approaching the asymptote. Or your numbers go from being very large to being very close to 0, which is what makes these both exponential decay functions. And that's the major difference, is when you look at a graph, if you were moving toward the asymptote from left to right, it's going to be exponential decay. Therefore, when you look at your numbers, when you plug in negative numbers, you get large things. Fractions to negative numbers become whole numbers, and 2 times 2 then became 4. But the larger and larger numbers I plug in, when I plug in something like 1, well, now I'm multiplying 2 by half. My numbers are getting smaller by 1/2 every time I move to the right, or I went from 4 to 2 to 1, and so forth. 3 may not look like it's going to decrease. Remember, the big thing I was looking at here was that 1/2 was less than 1. But 3 is greater than 1. However, to a negative exponent makes this a 1/3 to the x. Remember, negative exponents make reciprocals, and 1/3 to the x would become decay. So we're going 1/3 every time, or my y values go from being 3 to 1 to 1/3, and so forth. Smaller and smaller every time. And that's the major difference between exponential growth and decay. The base b, the number raised to the x down in the base, if it is greater than 1, you're going to have exponential growth. If it's between 0 and 1, however, you're going to have exponential decay, or you're going to move from away down toward the asymptote. Remember, your asymptote typically at y equals 0 for the horizontal asymptote. What happens if b is exactly 1? Well, then you get a constant function. You're not increasing or decreasing. You'd actually get a horizontal line. So therefore, we define decay as being between 0 and 1, and growth as being greater than 1. If it were less than 0, you actually get an alternating graph. Or if you look at your y values here, we went from positive to negative, back to positive, down to negative. We're not getting a smooth function. So just kind of two little side notes for you. Your b value can't be exactly 1 or exactly 0, or less than 0 for that matter, or you won't get a smooth function. Now, one of the things you'll be doing in your homework, more than likely, is classifying between growth and decay, as well as making simple graphs. And one easy way to do that, again, is to look at your base. Notice I don't have any negative exponents, so none of those tricky answers like the third one we did on the first screen there. But as 3 is greater than 0, this is going to be exponential growth. And as 1/2 and 2/3, the numbers that are raised to the x, are less than 1, these are exponential decay functions. The domain for each of these functions, because they're all exponentials, will be all real numbers. But the horizontal asymptotes are affected. Notice we do have a lot of shifting going on in these functions, a few different transformations. Remember, anything inside the exponent is going to shift you left and right. However, your horizontal asymptote can't be moved left or right. Horizontal lines moving left and right, you don't really notice the difference. Only if they're moved up or down. So like this -6 is going to move us down 6. So instead of y equals 0, it's going to become y equals -6. This -4 identifies that we'll have a horizontal asymptote at -4 or +2, so up at 2. We are going to move left and right as far as our points are concerned, but we're not going to move up or down, or left or right as far as our horizontal asymptote is concerned. Everything will move up or down, such as the horizontal asymptote. It also moves our range. However, for that, we're going to have to be a little bit more careful because one of these functions is actually also a reflection. You'll notice a +2 out in front of this function. So if we thought 2 times 3 to the x, ignoring the shifting, we would simply have a horizontal asymptote at 0 and exponential growth function. But instead, we're down 6 units. We're going to be left 2, so instead of being kind of simply on the y-axis, I would think over a little bit, but then increasing from there. So again, I'm going to kind of be working our way up through here. And again, that's just a basic sketch. You can always use easy points, such as we did with exponential growth, to find more accurate points. But notice that the range will be that y is greater than -6. Now this next function, notice, has a -3 out in front of it. So although we are going to be down 4 units for the horizontal asymptote, we are going to be shifted right 7 units. We're also going to be upside down. So when you plugged in a number like 0 in initially, without the -7 and -4, we would have gotten -3. But now we're also shifted down 4 units and right 7 units. So we're going to be kind of over in this area. And your function, if you found some more points, is going to still be decay. So I'm going to still work my way toward the asymptote, going sort of up that direction. But that means that my range is below, y is less than -4. Same thing goes for the last function. Again, you could type it in your calculator, but we're going to move up 2 units. But then notice a +5/2 out in front means that I'm still above the asymptote, and we're going to grow up this direction. Again, graph those on your calculator. They should look reasonably the same as what we drew down here. But keep your eye on that negative in front. If it's a negative a value, we're going to be below the asymptote. If it's a positive a value, such as 5/2 up here, we're going to be above the asymptote. Last thing for you is just to talk about how do we apply exponential decay functions. And a few of the different ways are given to you up at the left here. Radioactive decay, such as chemicals that decay away. Depreciating values, anything like a car that you buy that decreases in value. The value of money, such as inflation. Or also disease and epidemics. They may start off with a lot of people being sick, but then as time goes on, again, fewer and fewer people can be sick because they're more and more immune people. So disease and epidemic also relate to exponential functions. Well, if we're talking about exponential decay, it's going to be very similar to exponential growth. The value of something is given by its principal or initial value multiplied by that full value and its interest raised to the time, such as 6 years in the problem here at the left. The difference is going to be, we want to go down in value. We're going to depreciate by 34%. So instead of saying 1 plus my interest rate, something greater than 1, therefore growing in value, I'm going to say 1 minus. I want to make sure that my value goes down from that 12,500. Now realize your depreciation rate is 34%, but I don't want to know how much money I'm losing. What I really care about is how much is my car still worth. And if we take 1 minus that 0.34, you get 0.66. And that is how much money it's still worth. We're keeping 66% of the value. And if we type that into our calculator, very carefully, you notice I've got that typed in over here at the left, $12,500 times 1 minus 0.34 to the 6th gives you $1,033.17. So our value in just 6 short years dropped from $12,000 down to about $1,000 in value. Over here at the right, I've got another example of exponential decay. Notice this one, instead of being 0.66, our decay factor, our 1 minus r, is equal to 0.99987. So we're not going down by very much. It's just a little bit less than 1. But I can still use that function to find how much carbon-14, again, a radioactive element present in living things. That's why we always use radioactive carbon-14 or carbon dating, if you've heard of that before. in order to date functions, figure out how old they are. Well, if I have 45 grams of carbon-14, after 1,000 years, 45 times 0.99987 to the 1,000 will tell me how much will still be present after 1,000 years. And again, that's the number I have down below here. 45 times 0.99987 to the 1,000 is 39.514 grams. So even after 1,000 years, there's still a lot of carbon-14 left. We only lost about 5 grams out of 45 grams. So realize it's a very slow process. Thus, what lets us find the dates or ages of things like dinosaurs or really old clay pots from a long time ago. We can also use that idea backwards. How about if I know there's 10 grams still present, so I know that 10 equals 45 times 0.99987, but I don't know how old that is. How long will it take to go from 45 grams as principal down to 10 grams? Well, we can use a graph to accomplish that task. So notice on my screen here, I've typed in 45 times 0.99987 to the x, and I've also typed in as a second function just f equals 2, f of x equals 2. 10, sorry, f2 of x equals 10. And what I want to know is where those two lines cross. Now the first one, fairly easy to see, is up at 10. Notice my graph starts at 45 up here, which is my initial value. So a very thin blue line is present up here at the top of the screen. But it's going down so slowly, it's going to take me a while to figure out where those two things cross. So what I'm going to do is change my y values over here, knowing that it's going to take a long time. Well, in 1,000 years, we got down to 39. So my guess is something more like 10,000 years. 10, 1, 2, 3. In maybe 10,000 years, we might see something closer down to 10 grams. And it looks like we actually need to go a little bit farther. Notice the blue line and the red line haven't crossed yet. So let's try something more like 20,000. Almost got there. So if I go a little farther, there we go. And you'll notice I've already done the initial point of intersection. I can eliminate that though and remind you that in order to find that point of intersection, we're just going to go to Menu, Analyze Graph, Intersect, and then a little left bound, right bound. And you can find your point of intersection. So it looks like we cross our two lines at about 11,569.1. So after just about 11,569.1 years. Again, it takes a long time for things like carbon-14 to decay away. Last thing for you is just to discuss, what about that rate of decay? Remember I mentioned that the decay factor, remember, is 1 minus r? And that's what's present in our formula. So our factor, 1 minus r, is equal to 0.099987. So if I add r to the other side and subtract my rate over, you'll find out that r equals 1 minus 0.99987, or r will be equal to 0.00013, or approximately 0.013%. That again is your rate. This is your decay rate. So again, we're going down by a very, very, very small amount, less than, well, just barely more than, I guess, 1/100th of a percentage point, which is why it takes so long for carbon-14 to decay away. Hope that helps you understand how to use exponential decay functions, as well as some details about their graphs and what differentiates between decay and growth. Have a great day.